NAT is the ultimate duct tape of networking. NAT stands for Network Address Translation and encompasses an entire family of technologies. The recurring theme is modifying addresses in transit, something the OSI model creators didn't initially consider. The most common NAT deployment is to change the source IP address of a packet as it exits a corporate network out to the internet. This obscures the source IP address and also conserves publicly routable addressing, a resource in short supply with IP version 4 these days. Most organizations use private IP addressing internally as a result. The technology can be used for so many other tricks, such as translating destination IP addresses, TCP and UDP ports, IP version 4 into IP version 6, and many more. We'll focus on basic IP source NAT today. In real life, NAT is typically done on a router or a firewall. I'm showing a subset of the GlobalMantic network to illustrate how it works. In GlobalMantic, NAT runs on the firewall, which is convenient for a few reasons. First, it sits at the internet edge, so it can provide NAT service for the entire site. Second, the concepts of NAT inside and NAT outside align nicely with the concepts of firewall inside and firewall outside, respectively. This marks the trust boundary. Suppose the firewall has a public IP of 203.0.113.3 on its outside interface towards the internet. On the internet, the Google DNS server has IP 8.8.8.8, and host 1 still has IP 10.1.10.13. Next, the client sends a DNS query towards the DNS server. I'm color-coding the IPs to make this easier. No surprises yet. The NAT device will translate the source IP from 10.1.10.13 into 203.0.113.3, making the DNS server think that the firewall originated this packet. When the DNS server responds, it does so by targeting the firewall as its destination. The DNS server has no idea about the GlobalMantic client thanks to NAT. Upon receipt, the firewall uses NAT to change the outside destination address back to the client's IP. The NAT process is smart enough to check return traffic against its state table to ensure the NAT process occurs correctly in both directions. Let's explore a DNS exchange with NAT thrown in the mix. Before NAT occurs, the source IP of the DNS query is 10.1.10.13, the GlobalMantic host 1. The destination IP is 8.8.8.8. Note the DNS transaction ID of 4E7C because it's going to be relevant soon. Here's another capture of the same packet after NAT occurs. After our firewall performs NAT, the source address changes to 203.0.113.3. This means the DNS server and anyone else on the internet will see all GlobalMantic traffic as originating from this specific IP. Even though the IP header has changed, the DNS query has not, as evidenced by having the same transaction ID after NAT occurs. I used a type of NAT here that hides many source addresses behind this one IP using a technique called NAT overloading. It often uses layer 4 information like TCP and UDP port number to track different flows. We won't dig too deep into that. My point is that our payload integrity is maintained across NAT.